Now let's move on to something else, which is the SNR. The SNR is the signal to noise ratio. All right, let's make clear on something. There is RF everywhere. The universe is radiating RF, and that was measured a century ago. And there is a clear measure of that energy coming from space. And if you look at a 20 megahertz channel, if that doesn't mean much yet, it will mean much very soon. If you look at a 20 megahertz channel, that represents about minus 101 dBm. So we already have some noise in the background coming from the heat of this planet and all the radiation of the universe. Of course, human activity adds a lot to that. All that activity, which is RF energy we don't care about, we typically call that noise. You'll hear also background noise. Background noise, when you want to distinguish what is the surrounding noise from a source, a very specific source that is damaging your signal and that you cannot identify. So that would be noise, but not coming from the background, coming from a specific source. But if you generally say noise, it's pretty much everything altogether. Okay, so why do we care? Because, of course, if you speak in a room that is very quiet, you can whisper and you will be heard. But if you speak and you whisper outside in the streets, very noisy with buses, you will not be heard. So the RSSI is very important because it measures the loudness of your voice, that is to say, the amount of energy you're receiving. But there is another factor that is important, which is how much louder than the surrounding noise your voice is. If the surrounding noise is very low because you're in a quiet room, the RSSI may give you the amount of energy, but you'll know you'll be able to use that energy. If that same energy is measured outside, then it won't be enough anymore. So the RSSI is important, but it's always important in combination with the SNR, which measures how much higher than that noise level your signal is. The two work together very closely. Most circuits will be designed to be able to use a certain signal, RSSI signal, and read zeros and ones out of it. But that is assuming a certain maximum noise level. So it's going to require an SNR value minimum of X and an RSSI minimum of Y to be able to receive and interpret signals. So typically when you represent those, you typically represent the signal strength on the vertical scale and then time on the horizontal scale. And then you have one line, which is basically the signal you receive, the useful signal. And if you measure that signal strength, you'll be measuring the RSSI. And then there is the surrounding noise around, right? That is damaging partly that wave. And if you compare the two, you'll be using the SNR scale. Let's take an example. You have a signal that you receive at minus 76 dBm. Your environment is not purely quiet universe, so it's not minus 101. You're receiving some noise from other sources, and your noise floor is at minus 97 dBm, which is kind of common. In many building environments, you assume a minus 94 to minus 95 noise floor, so minus 97 is a pretty nice environment. Okay, so what is your SNR? Well, your SNR is simply one minus the other. So it's minus 76 minus 97, and of course minus means plus 97, so your SNR is going to be plus 31 dB. Plus 31 dB means that your useful signal is 31 dB above the noise floor. It doesn't give you the measurement of how much energy you're receiving, you need the RSSI for that. But it tells you that that signal you receive is 31 dB higher than the noise. And of course, depending on what you try to achieve, that could be good, that could be bad. Typically 31 dB is very good. Something below 10 dB is typically a problem. A good condition is anything above 20 dB, so 30 dB is a pretty good number. So that was the noise, but as you work in a Cisco environment, you will hear about noise and you will also hear about interference. So this is different.